This is problem number 19 from section 3.5. We are given our matrix, we have a linear system, we have our characteristic polynomial, we find two distinct real eigenvalues. One of them is 0, lambda 1 is 0, lambda 2 is a 5. I won't go through the calculations of finding the corresponding eigenvectors, but you can check that 1 minus 2 is the eigenvector for lambda equal to 0, and 2, 1 is the eigenvector for lambda 2 is equal to 5. In part C, we're asked to draw the phase diagram. I've already gone ahead and written the general solution, but here's our phase diagram, and here's how it's drawn. We take our two directions, our v1 direction and our v2 direction. The direction corresponding to the 0 eigenvalue, every point on that line is an equilibrium point. And of course, 0, 0 is on that line. 0, 0 is an equilibrium value for every linear system. Okay. So if you were to start at a point on this line, you would not move. You would stay on this line. You're an equilibrium solution. I can verify that quickly. I'll do it later. Okay. So that's the first part. The second important part of our phase diagram is the second direction. And in this case, because lambda is positive, everything in this direction is moving away from the origin. So if you are to start at a point, for example, in the next section they say, well, suppose you're at 1, 0. What is happening? Well, as time moves forward, you will move away parallel to the v2 direction. And as time moves backwards, you will have come from the line, corresponding point on this line, the line given by the eigenvector v1. Following that model, to complete the phase diagram, everything is moving away from these equilibrium values. They're all sources. I'll draw the corresponding arrows to indicate that we're moving away, but in a direction parallel to v2. And that's our phase diagram. I would like to see in part D, they say sketch the x of t and y t graphs with initial condition 1, 0. So let's do that. So here's part D. What we observe from the graph, if we're starting at 1, 0 and we're moving away, so if I were to draw the x graph, you might want to draw it linearly, but we can see in the general solution that our x component is growing exponentially, and so it makes sense that we're going to be drawing something. In fact, it's e to the 5t, so it's going to be growing quickly, and so a rough picture would mean that for the x graph we start at 1 at time 0 and we grow exponentially. For the y graph we start at 0 and we grow exponentially. What's interesting, however, is as time moves backwards, what is happening in this situation, the x value is not approaching 0. You can see that the x value is approaching some non-zero value, and I'll talk about that in a second. So the x graph is asymptotic to some value above 0. I'll draw the y-graph in red. And the y-graph is also going to be asymptotic to some value. We can see as time goes backwards, we're approaching some known point here. It turns out that this value is going to be negative 1/5 for y, and I'm sorry, negative 2/5 for y. It's awfully sloppy. Negative 2/5 is the value that the y approaches, and the x value approaches a value of 1/5. And the reason for that is we have two perpendicular lines, the to one direction and the 1 minus 2 direction are perpendicular to each other. If I find the intersection of the line passing through 1, 0 with a slope of 1/2, intersecting the line passing through the origin with a slope of -2, I see that they intersect at the point x is 1/5 and y is negative 2/5. And you'll see, as I will now write out the particular solution in part F. I believe in part F, yes, we're asked to find the particular solution. So I say, well, y at 0 has to be a 1, 0. That gives me a k1 times 1 minus 2 plus a k2 times a 2, 1. I get the statement that k1 plus 2k2 is a 1, and a minus 2 k1 plus a k2 is equal to a 0. I've done these out, and you will see for sure that k1 ends up being 1/5, and k2 ends up being minus 2/5. I take that back. K2 is positive 2/5. I'm going to move over to here and write this out more clearly. Our particular solution, y of t, has a 1/5 times a 1 minus 2 plus a 2/5 e to the 5t times 2, 1. If I group terms together, I have a 1/5. I'm going to write that a little higher. I have a 1/5 and a minus 2/5 plus 4/5 e to the 5t plus 2/5 e to the 5t. I don't know how easy it is for you to appreciate that certainly as time moves forward, we are following e to the 5t. We're starting at 1 and we're growing. And this also, the y value is growing exponentially. It's starting at 0 and it's growing. But as time goes backwards, as t becomes negative, these terms go to 0. This term and this term goes to 0, leaving me at, so here I am at time 0, minus 1, minus 2, going to minus infinity. I'm approaching this line. What point do I approach it at? I approach it at the point, I'm approaching the point 1/5 minus 2/5. Okay? I hope that helps. Good luck.